Hello everyone, we are Team AMBATS Part 2, sponsored by EaglePicher Technologies. My name is Anissa Elias and I would like to introduce you to our project on the Advanced Modular Battery System. Our technical directors for this project are Frank Puglia, the Director of Research and Development at EaglePicher, and Daniel Wirtz, a Senior Level Systems Engineer also at EaglePicher. Our team consists of myself, Anissa Elias, a computer engineer, Christopher Sharon, a computer and an electrical engineer, Sean Thurber, an electrical engineer, and Nicholas Dort, an electrical engineer. With its headquarters in Joplin, Missouri, EaglePicher specializes in providing battery solutions for very demanding applications. They are a leading producer of state-of-the-art battery technology for aerospace, defense, aviation, and medical applications. Batteries EaglePicher has produced have been used in many notable instances, such as providing the emergency power for Apollo 13, powering the International Space Station, powering the Mars rovers, military jets and helicopters, as well as life-saving medical implants and more than 85% of U.S. missile platforms. Now, the motivation for this project is to deliver the performance that EaglePicher customers demand and require. As EaglePicher provides solutions for very demanding applications, their batteries need to withstand the test of time and the harshest conditions. Having a battery management system with the ability of collecting high-fidelity performance telemetry could prove invaluable in evaluating battery cell design. Ultimately, having this smarter battery management system will allow individual product maintenance via a check engine signal, avoiding instances such as the current product recalls costing the industry billions of dollars. Now, for our anticipated best outcome, Team AMBATS has two parts. First would be creating a fully functioning battery testing system to measure all important parameters of our battery pack. This battery pack consists of 12 18650 lithium-ion cells, all connected in series. The testing system consists of a commercial off-the-shelf battery management system and a real-time data acquisition system, as well as a BK load used and configured to different load profiles. Now, the second part of our anticipated best outcome would be the software. A digital twin was created to simulate real battery data, and with that data, we created an optimizer machine learning model to fit the data and tell us which parameters are most important in real-life applications for real-time alerts. To be able to create the best possible testing system, our team had to build up an extensive background in battery chemistry and battery behavior. After understanding all the background information, we were able to select our key components and make a long-term plan to make sure the testing system works by the end of the year. Then the hardware team began working on creating the PCB that would tie all the components together and created a plan for getting the testing system ready for assembly. Once all the components arrived, they were able to put everything together and create what we have now, which is a fully functioning battery testing system. Now, for the software team, as we weren't able to output data from the testing system in time, a battery digital twin data simulation was created and multiple data sets were generated from that digital twin. All this data was then passed through a normalization function to eliminate any anomalies within the data set that would negatively impact the learning of the models. Then, using TensorFlow and Keras, said machine learning models were created, trained using the normalized data, and then they were able to give us our desired output of fitting equations for all datasets used. This product would set EaglePicher up to be able to advance their studies into the usefulness of worn batteries and what they can be used for after their primary use has been exhausted. The technology would be capable of being mass-produced and be capable of detecting damaged or malfunctioning battery cells that otherwise would not be able to be diagnosed in the field. By optimizing the battery management system around the most important parameters to measure for both safety and state of health and charge, EaglePicher Technologies will be able to set the standard for providing rapid solutions for critical applications. Now for a more in-depth discussion of our technical accomplishments, I will be talking about how I took over for the software team and created our machine learning models. Our goal was to understand what parameter might be the best in analyzing battery health and damage. The steps we took to get there started with generating battery parameter data from our digital twin. I then normalized the data being output as there was a 16:1 noise-to-signal ratio. Then, that normalized data was used to train the stochastic gradient descent models built, and when those models were trained with minimal loss, they output a fitting equation that gave us our answer. Starting with the generation of data from the digital twin, the picture on the left shows what a dataset of state of charge versus battery error looks like. As there are no clear patterns for the models to learn from, I needed to find a solution for normalizing this data. Therefore, a function was created to iterate through each dataset I would use and delete all entries with a damage that would make a cell unusable in real life. This resulted with datasets like the picture on the right, which was more useful for the models overall. And this is another example of using that same function to iterate through another dataset of temperature versus error and delete all data points that wouldn't be useful for the models, resulting in the picture in the right with a clear curve. Now, as we are trying to find the most optimizable parameters at their minimum, the best way to do this was using a stochastic gradient descent method. So, using TensorFlow, I successfully employed a stochastic gradient descent model and used mean squared error as the loss function to calculate loss while the model was learning and training using our data. Now, to get our results for the fitting equations, there needed to be many sessions of training the models to be able to minimize the loss and output a fitting equation. These two graphs show just a few of the sessions doing just that. The different profiles output a stark difference when it came to minimal loss that could be achieved by the model, which in turn greatly affected the fitting results and gave us a better understanding of which parameters would be the best used. First, we have the most normalized data out of the 6 profiles. These were individual data readings with no outside interference and no load profile. The model was able to learn great from them and output a near perfect fit. This was a quite noisy load profile. The batteries here are simulating an electric vehicle battery driving from East Greenwich here to URI. The models were still able to get a nice fit with a close local minimum, but with the state of charge and temperature data sets having the same profile, we can start to see that the temperature might be a better indicator for when things start to go wrong. Now, this is a state of charge and temperature with outside interference and a driving profile of the electric vehicle battery. As we can see, it's getting much harder to fit the state of charge data, but there's still a nice curve for the temperature. Lastly, this is the most noisy data from the digital twin, and this is it even after being normalized. This is with outside interference from cell resistance, state of charge, temperature, and with that same driving profile. But even with all of that, we can still see that this model was able to give a somewhat feasible curve for the temperature data, while missing it completely for state of charge and resistance. This can tell us that temperature might be a parameter that would signal a change in cell health much faster than any other. And when this is used in real-life applications, temperature can be the first indicator for when things can go wrong. Now moving on to the hardware part, Christopher Sharon will start it off by talking to us about the PCB and the assembly.
My focus has been on creating the printed circuit board used in our test fixture. Shown here is the schematic for said PCB, which we have dubbed the battery board PCB. The PCB was designed to allow the collection of cell data by both the data acquisition unit and the battery management system. This data includes the cell voltages, temperatures, and current. The PCB acts as a way to hold the cells in place, and it contains all circuitry required to collect and output the required data. Most circuitry required to collect the cell data for the BMS is internal to the unit, so all that is needed is direct connection to the thermistors and voltage taps. The current measurement is done entirely off-board as part of the BMS wiring harness. Here's what the board looks like. The cell holders are mounted directly to the board, which limits the variability in data measurement. This board routes the proper DAC and BMS connections to headers on the left and right sides of the board. The battery main positive and negative are also routed to a header, which allows connection from the battery cells to the load and charger. Containing all of these connections within a PCB has the added benefit of creating a much neater fixture and allowing for an effortless setup. Because all of the cells in the battery pack are wired in series, the common mode voltage when measuring the cell voltages differentially increases as the cells get farther from the main negative. This becomes a problem as we have 12 cells, so the voltage reading of the 12th cell could have a common mode voltage upwards of 48 volts. This is far above the voltage specification of the data acquisition unit, so we use differential amplifiers to remove the common mode voltage and measure the cell voltages with respect to ground. The output of the differential amplifier is fed through a burden resistor for measurement, which is needed because the DAC inputs are high impedance. A differential amplifier circuit is needed for every cell to ensure consistent measurements. These circuits are located on the bottom of the board, along with the low dropout voltage regulators used to power them. We are only using voltage modules for our data acquisition unit, and one of the challenges of doing so is that signal conditioning is needed to allow measurement from our sensors. This circuit is a voltage divider that allows for temperature measurement from the thermistor sensors. A thermistor is used as one of the resistors of a voltage divider, so the voltage at the output will change with respect to the temperature. Based on the characteristics of the thermistors and the components used in the circuit, I was able to define a formula that will provide the temperature of thermistors by reading the voltage across them. The 12 thermistor voltage dividers are located at the bottom of the board next to each of the cell negative terminals. A cutout is made in the board to allow the thermistors to be positioned to touch the cell and ensure the most accurate measurement. The thermistors used by the BMS are located in the same manner, however no extra circuitry is required on the board. To ensure consistent thermistor positioning and to be able to affix the PCB to the test fixture, I designed this base assembly. Here is a rendered version of the PCB assembly, including a cross-sectional view to show the thermistor locators. The base has raised protrusions located at the cutouts of the board that are used to hold the thermistors from both the DAC and BMS in place. Nick will discuss more about this mechanism later in the presentation. The PCB assemblies are designed to be swapped easily as everything is self-contained and all connections unplug. This is so different battery packs can be assembled and swapped out without having to replace all of the individual cells. After soldering the board and 3D printing the base, the completed PCB assembly is shown here. The board is fully functional and has allowed us to collect multiple datasets. Our next designer is Sean Thurber, who will tell us about our analog load circuit, wiring the battery management system, and data collection and evaluation.
Part of the initial plan was to build a programmable load profile circuit to create dynamic discharge profiles to apply to the battery pack. This is an expansion on the initial draft and calculations provided by Dan Wertz. A logic driver is used to control a clamping circuit, which would drop the gate voltage of the transistor connected to the bulk resistor, thus closing the load channel. With 8 channels, an 8-bit digital signal is used to switch each individual channel on or off, which would allow for 256 steps between 0 and 10.24 amps. With a reference voltage of 100 millivolts, resistor values are calculated to match this voltage on the negative feedback of each channel. These resistor values were adjusted for standard values, and a variable trim resistor provides fine adjustments. Power dissipation is calculated to ensure components purchased can handle the power through them. A simulation was performed in multisim with non-ideal components. Earlier simulations had transient current spikes at the edge of each load change, which are now gone. However, the maximum current drawn on the highest channel is around 4.35 amps, below the 5.12 amps expected, which could partially be due to models chosen for non-ideal components. After the acquisition of a programmable DC electronic load, this load profile circuit was repurposed as a backup plan, but was never fully completed. There are inherent limitations in an electronic load that limit the type of load profiles that can be applied, and it may be that building a load profile circuit is the better option, so hopefully the work done here will be helpful for future work on the project. A minor contribution I made to signal conditioning on the PCB was for the National Instruments DAC current sensor. The current sensor chosen is the LEM LA205S. It has a 1 to 2000 conversion ratio and requires an external resistor to set a voltage scale to represent the current passing through. The formula shown will provide the current as a 10-volt scale for 10 amps with a 50% margin. A major part of getting the test platform up and running was the wiring for the Orion battery management system to the PCB. It's vital that each connector is wired correctly so that it matches the pinout of the header on the PCB to avoid potential damage to the system. These connectors had to be crimped by hand, and with so many chances for error, I decided to draw up a wiring diagram for all connectors in Microsoft Visio and number them to save myself some heartache. I didn't stop there though. I drew a wiring diagram for just about every connection of the test platform as well. This reflects the current state of the test platform and includes connections to the power supplies, electronic load, and CAN bus network to the laptop used to collect data. Here's a comparison to the actual test platform. We cleaned up the wires as best we could with the time we had left, but outside of that, it lines up fairly well with the diagram. The last contribution I made was the synchronization and evaluation of the data through a MATLAB script from charge and discharge tests run on the battery pack. Shown here is a flowchart which outlines the process the script goes through. The script loads the data logs and synchronizes the data to start at a quick initial 1 amp discharge pulse added into the load profile program to the electronic load. On the right in the boxed off section is an example of a loop subprocess in the script. There's one of those for each blue block, so only one is shown here as an example. The Orion BMS collects around 10 samples per second, while the DAC collects 5,000 samples per second. The point here is to compare the data collected on the cell voltages, current, and temperature from both of these systems, and see if a standard battery management system is missing any important information in its data collection that would be important in determining the state of health of a battery. The script evaluates the data and plots the cell voltages and current in a stacked plot, which allows a user to see all data values at any timestamp by hovering the cursor over any section. The plot shown here is for the data collected from the Orion BMS on a 30-minute test. Shown here is a plot of the data collected from the National Instruments DAC on the same test. As noted earlier, the current sensor for the DAC reads current as a voltage over a burden resistor, and so needs a formula to convert the voltage values to current values. There is also a voltage offset present in the current sensor, which is impacted by movement of the wire through the current sensor and the magnetic field from the contactor. A linear fit approximation can be used to convert the voltage values to current and account for the voltage offset by comparing the DAC current sensor readings at each current step in the load profile seen on the x-axis to the current measured by the BMS seen on the y-axis. The script detects the transitions in current and saves all data at each of those points and automatically derives a conversion formula for the DAC current sensor that also accounts for the voltage offset based on the data present in the log files. In the future, it's recommended to add a burden resistor in series with the wire to the battery pack to get an accurate reading of the current, which would help in calibration of the DAC current readings. Finally, the script calculates the cell resistance values by the change in voltage over the change in current at each step of the current load profile. When comparing the ability of the Orion battery management system to calculate cell resistance against the National Instruments DAC, it can be seen that the battery management system drops data and is missing important information. Cell resistance is one of the best ways to determine state of health of a battery and is one of the most sensitive methods to detecting anomalous aging of cells. These results show that there is data present in high-fidelity data collection of cells, which is vital to determining the health of a battery that is not present in typical battery management system data collection. There is much more to be investigated. However, with all this information, we can say that we have met our ABO for this year and can pass on useful data and hardware to the next team to continue the project. Our next designer is Nicholas Duarte, who will tell us about the 3D printed holders for the thermistors in the PCB platform, thermal data collection, and the programming of the electronic load in National Instruments DAC for running charge and discharge tests.
Hello there, I'm Nick, and I'd first like to talk to you about the advancements that we've made with the thermal capabilities of our board and how useful they can be in detecting bad connections, faulty cells, and the overall health of the battery pack. To the left is an example of the thermistor nest that we modeled and created on the 3D printer. As you can see on the right, those slots are the perfect size for the thermistors that we purchased to detect thermal changes that the cells undergo as they go through the charging and discharging cycles. This next image is an example of the dashboard of our data acquisition system. As you can see, both voltage and temperature taps are labeled and connected to each cell, and we can monitor and record the information coming from each cell from this screen. This is the screen that we see when we are setting up our load profiles. On the left, you can see the amount of load in amps that the cells are under and the length of time in seconds that the load is held for. The next few slides are dedicated to thermal images that I took using a thermal camera provided by the EaglePicher technical directors. Starting on the left, you can see the cells at room temperature before the cycle has begun. The two hot spots that you can see on the left side of the board are of the power converter and some components on the other side of the board. As time goes by, you can see that on the right, some of the ends of the cells are heating up. Those are anodes, or the negative ends of the cell, which generally heat up before the cathodes, or the positive ends of the cell. As the test continues, you will notice that on the left, some cells are heating up faster than others. On the right, it is very obvious which cells are getting hotter than the rest. The faulty cell that we planted in this experiment is the one in the top row in the middle, but that is not the only cell that seems to be having thermal problems. The two packs on the left side of the board also seem to be heating up. After a discussion with our technical directors, we came to the conclusion that the reason for these cells heating up faster than the others is that the physical connection that they are making with the board was faulty and was later remedied by using a compound impregnated with silver to increase the electrical connection between the tabs of the holder and the cell itself. This final set of thermal images show the cells at their peak temperatures. This thermal information can be extremely useful in determining which cells in a battery pack have problems, like if they're heating up faster or slower than the other cells in the pack. The abnormal cells are clearly visible and can be isolated for further study. Finally, I'd like to summarize the anticipated best outcome that we achieved. We designed and built the test platform used to collect data on the lithium-ion cells. We collected and synchronized cell data for analysis. We determined that high-fidelity data collected through the data acquisition system is vital to determining the health of a battery and is not present in typical battery management system data collection. And we optimized machine learning models of generated data created to understand the relationship between battery parameters and the damage that batteries endure in various conditions. We would also like to thank some very special people who have helped our team tremendously. Frank Puglia and Dan Wirtz, our technical directors at EaglePicher Technologies, Dr. Sunak, our Capstone director, and Dr. Zhang, the professor whose lab we took over and used for all of our experiments. Thank you all very much.